Okay, let's jump right into this explainer and look at why your code might be consuming way too much memory, and more importantly, how we can actually fix it. We're going to completely demystify a concept that is absolutely essential if you want to write truly professional, scalable software. So picture this. You've just written a script and it executes perfectly. I mean, it's lightning fast, the logic is totally flawless, but then out of nowhere, boom. Your computer just grinds to a complete halt. Or even worse, the whole application just unexpectedly crashes. Why does this happen? Well, it all comes down to the invisible burden of memory usage. You see, execution speed is really only half the battle. If your program is fast, but it literally eats up all your system's RAM, it's going to fail, period. And this brings us to our core concept for today, space complexity. In plain English, this is just the total amount of memory an algorithm needs to run, specifically as the input size grows. It basically measures the physical footprint of your program. And honestly, it is so crucial that tech giants like Google and Amazon absolutely obsess over it during their engineering processes and technical interviews. Efficient memory management is what separates an amateur, messy script from highly polished, enterprise-grade software.
To tackle this, here's our roadmap for today. We'll define the memory problem, compare fixed versus variable memory, measure space with big O notation, check out the hidden traps of recursion, explore real-world management, and then wrap up with 5 tips to optimize your code.
All right, Section 1, the memory problem. Let's start with a really relatable analogy.
We've all been there with a struggling smartphone, right? Think about everyday apps like YouTube or Instagram. When you're scrolling on your phone, you only have a very restricted, limited amount of RAM. If the software is hogging memory, the results are immediate. Your device suddenly feels like it's trudging through molasses, apps randomly crash, background servers get totally overloaded, and your battery just plummets. Proper memory management is what keeps software running smoothly, even on a tiny device sitting in your pocket.
Moving on to Section 2, fixed versus variable memory. Let's pop the hood and see where that memory actually goes.
Every single program uses memory, but it essentially splits into 2 distinct camps. First up, we have fixed memory. This is your constants, your simple variables, the basic program instructions. This stuff basically stays put, its size never changes. But then, we have variable memory. This is the wild card. We're talking dynamic arrays, lists, and recursive calls. Variable memory balloons dynamically depending on your input size. So if your data goes from 10 items to 10,000 items, your variable memory requirement is going to scale right along with it. So, Section 3, measuring space using big O notation. How do we actually track this?
Well, the absolute holy grail for memory efficiency is constant space, or O of 1. This means your memory usage stays completely fixed, no matter how gigantic the input size gets. For example, if you're just using a couple of basic variables to, say, keep a running total, which we often call auxiliary space, your footprint stays incredibly small and efficient. Whether you are processing 10 items or 10 million items, if you only need one extra variable, your auxiliary space is rock solid and constant.
But things change when we hit linear space, or O of n. Now your memory usage is growing perfectly in step with the input size. Imagine a standard one-dimensional list. If your input size is 10, you need physical memory for 10 elements. Input jumps to 1,000? Now you need memory for 1,000 elements. It's a totally direct one-to-one relationship.
But you really have to watch out for quadratic space complexity, or O of n squared. This is where things get out of hand super quickly. A single 1D list is fine, it just grows linearly. But a 2-dimensional array like a matrix, it literally explodes exponentially. An input size of 10 suddenly takes up 100 spaces in memory. Bump that input to 100, and wow, you now need 10,000 elements of space. It consumes massive amounts of physical memory so incredibly fast, which is why you have to be super cautious with nested data structures.
And that brings us to Section 4, recursion and call stacks, the hidden memory trap.
Recursion is sneaky. When a recursive function calls itself, it isn't just looping in place. It's actively chewing through memory using the function call stack. Every single time it calls itself, it slaps a brand new physical block of memory right on top of the last one. It has to keep all those previous calls frozen in memory until the whole chain finishes. If that stack grows too deep, it topples over. And yup, you guessed it, that is exactly what triggers the dreaded Stack Overflow error.
Section 5, real-world management. How do massive systems survive without constantly overflowing?
It all boils down to the time-space trade-off. Developers are constantly walking a tightrope here.
On one side, you can deliberately burn extra memory to get faster execution speeds. That's exactly what caching is. But on the flip side, you can sacrifice speed to save precious space, like using data compression, which shrinks the footprint but takes way more processing power to unpack. It's a constant balancing act based on the hardware you're dealing with.
Think about heavy mobile video games. The developers building those have to carefully optimize memory to juggle some really demanding assets. They are cramming high-resolution graphics, huge sound files, and complex animations into a tiny phone, all while responding to your rapid taps without dropping a single frame. It is a masterclass in space complexity management. Companies like Apple and Samsung pour millions into their OS just to handle this exact memory dance smoothly.
Finally, Section 6. 5 tips to optimize your code right now. Let's shrink that footprint. Number 1. Ditch the unnecessary temporary variables. 2. Pick efficient data structures. Actually, scratch that. Make sure you pick the right ones. Don't use a massive 2D array if a simple list does the job. 3. Try to use loops instead of deep recursion to avoid stacking up all that memory. 4. Modify existing data to reuse memory rather than spawning new arrays. And 5. Proactively delete unused data and objects. Stick to these and your programs will run incredibly lean.
Ultimately, keep this idea in mind. A lightning-fast program is absolutely useless if it eats all your system's memory. Modern software engineering isn't just a race for speed. It's a really delicate, thoughtful balance of speed, scalability, and physical memory footprint. Mastering that balance is exactly what will make you stand out in a technical interview or on the job.
So, as you head back to your IDE today, I want to leave you with a question to chew on. Which part of your current code base is quietly eating up all your memory right now? Keep an eye out for those nested arrays, double-check your recursive loops, and always ask yourself how you can better balance execution speed with physical space. Thanks so much for joining me for this explainer, and happy...
If you enjoyed this video and learned something new, like this video, comment your favorite programming language, subscribe to Future Break Coder, because many exciting coding and futuristic tech videos are coming soon.